Hello everyone, welcome back to the third lecture in this series. So we have already seen in our previous two lectures why we need to convert from NFA to DFA for creating our lexical analyzer or scanner. And we have also seen how to compute the epsilon closure for the states of an NFA. So today let us look at the algorithm for performing the conversion from NFA to DFA. So the steps are something like this. The first step is what that we have to do is that we have to compute the epsilon closure of all states of the NFA. So given an NFA, we have to find the epsilon closure of each of the states and write it in the form of a table. Next, what we will do is we will take the epsilon closure of the start state of the NFA to be the start state of the DFA. Let us call it A. Let us call this state A. I think this will be better understood if I take an example. So let me take an example here. So I have a NFA, which is something like this. Let me start with a simple one. So I have 1, then I have state 2 here, state 3, and the final state 4. Okay, and my transitions are like this. This is epsilon, this is an A, this is an epsilon, then from 3 on epsilon it goes to this, and 1 on epsilon goes to 4. So if I have to, first step is step 1, compute the epsilon closure of all the states. So my states are this, and this is the epsilon closure. So state 1, 2, 3, and 4. So for 1, the epsilon closure is 1 on epsilon can go to 1, it can go to 2, and it can go to 4. Similarly, 2 on epsilon cannot go anywhere else other than 2 itself. 3 on epsilon can go to 3, it can go to 2, and it can go to 4. And 4 on epsilon cannot go anywhere else but itself. So we have performed the first step of our algorithm. That is, we have computed the epsilon closure of all states of the NFA. Now, we have to take the epsilon closure of the start state of the NFA. So the start state of the NFA is this one. This is the start state. So we have to take the epsilon closure of this. Okay, let us call it the set A. Now this set A would be the starting state or the start state of our DFA. So our A is the set 1, 2, and 4. Okay, so this state is this new state A is actually the set of the states 1, 2, and 4 of our NFA. So this whole thing would be the start state of our, this will be the start state of our DFA. So we have done the second step. So if I go back to the algorithm, so take the epsilon, second step says take the epsilon closure of the start state of the NFA as the start state of the DFA and call it A. Then we have to go to the third step. In the third step, what we do, find the transition on all input symbols for A. So we have to find the transitions on the set A for the input symbols of the language. So coming back here, so I have my state is A, state is A. So there is only one input symbol you can see in the NFA, it is A. So our language consists of only one input symbol A. So we have to find the transition. We have to find the transition on A, capital A, which is the set of states 1, 2, and 4 on the input symbol A. So how do we compute this? The steps are given out here, here, and here. So I have the DFA transition on A, on capital A, that is the set of states, on the input symbol small a is, how do we compute it? It is the epsilon closure of the NFA transitions of A and A, of the set A on the input symbol A. So how do we get this? So first of all, we have to see that for the set A on input symbol A, what are the transitions? So for that, again, let us go back here. So if you see in this set A, I have 1, 2, and 4. So in our NFA, let us see on 1, if I get input symbol A, what is my transition? Nothing. Okay. On input symbol 2, what is my transition? It is A. Okay. I think this would be more clear if I draw the state transition table for the NFA. So let me draw the state transition table for the NFA like this. So my state is here, my transition on input symbol A. So I have 4 states, 1, 2, 3, and 4. 1 on A doesn't go anywhere. As you can see, 1 on A doesn't go anywhere. 2 on A goes to 3. 2 on A goes to 3. 3 on A does not go anywhere. 4 on A also does not go anywhere. So 3 on A doesn't go anywhere. 4 on A doesn't go anywhere. So now what I have to do is I have the input symbol A, sorry, not the input symbol, the state A, which consists of the states 1, 2, and 4. So this is our NFA transition table. Now I have to create the DFA transition table, starting with this state. So 1, 2, and 4. So on A, I will see the transition would be the union of transition on 1 on small a, 2 on small a, 4 on small a. So 1 on small a is this, 2 on small a is this, 4 on small a is this. So what I have in all of this, the union of all of this is 3. All I have is 3. So out of these 3 states, I get that only on state 2, there is a transition to state 3 on input symbol A. So I will take the, what will I take? I will take the epsilon closure of 3. So I'll take epsilon closure of 3. Okay, so that will be my transition here. So let's see what was the epsilon closure of 3. Epsilon closure of 3 was this, 3, 2, 4, or 2, 3, 4, any way you want to write it. So we will write it here, 2, 3, and 4. So this would be, epsilon closure of this would be 2, 3, and 4. So this will be the transition, or the DFA transition on the start state A. That is 2, 3, and 4. Okay, so I have this. Now I have in my DFA table, I have got one state, that is 1 to 4, and I have got another state here called 2, 3, 4. So this is a new state which has appeared. So next step, what I'll do, I will find the transition on 2, 3, and 4. So 2, 3, and 4. This will be my new step. Now on this state, I will try to find what is the transition on the input symbol A. So again, if you see 2, 3, and 4, 2 is this, 3 is this, 4 is this. So It's the same union of all this, that is 3. So again, the transition, DFA transition would be the epsilon closure of 3, which is 2, 3, and 4. Now, have we reached a new state? No, we are still in the old state. 2, 3, 4 we have already encountered before. So this is where we stop. So now, if you see, we have reached the transition table of our DFA. So I have, in my DFA, I have 2 states. The one state is the combination 1, 2, 4, and the other state is 2, 3, 4. So I can draw it like this. I can draw it like this. One state will have 1, 2, 4, and other state will be 2, 3, 4. Okay. What is that? Which is the start state? This is the start state. 1 to 4. 1 to 4 is the start state here. Okay. So 1 to 4 on A will go to 2, 3, 4. 2, 3, 4 on A will remain on it in itself. Okay. So 2, 3, 4 on A will remain here. Okay. Now, which is the final state? The final state would be the one according to our algorithm. The final state of the DFA is the state that contains the final state of the NFA. So our NFA final state was 4 here. So in our DFA, our final state is contained in both of this. So this and this, both of these two will be our final states. So 4 is our final state in the NFA. Okay, so both the states 1 to 4 and 2, 3, 4 contains the state 4. So our DFA now looks like this. So if you try to interpret this, you see any string, the moment it starts without consuming any input symbol, it is accepted. Okay, because the first starting state is also this final state. So our epsilon is accepted, empty string is accepted. If I get an A and I get any number of A's, that is accepted. So epsilon or A plus. So either I can write this can be written as A star, that is 0 or more A's, that is accepted here. So if you look at our NFA out here, isn't this the same? So it accepts the very first without consuming any input symbol, it goes to this last state, final state. Okay, so epsilon, it accepts, and then also if you see it takes a single A, and then it can keep on repeating this A. This is for repetition. So any number of A's, so 1 or more A's. So that is our A star. So the NFA that we have here is equivalent to the DFA that we have got out here. So this is the conversion process. In the next video, we will take another example and we will see the conversion again.